All right, so starting chapter 3 off here, we're going to be getting into exponentials and logarithms and all that it entails, but starting off with exponential functions. The distance s a body falls from rest varies directly as the square of time t of the fall. If skydivers fall 64 feet in 2 seconds, how far will they fall in 4.5 seconds? So we're doing variation here. So it's going to be direct variation. So we're going to have s equals k t, and it's squared because it's the square of time. So because it's direct, they're both up there, both on the top there with k. K is going to be our constant. We got to solve for it first. It says skydivers fall 64 feet in 2 seconds. So s is our position, that distance it's fallen. So 64 equals k. Our t is 2, and it's squared. So 2 squared would be 4. So technically 4k. We're going to divide by 4 to get to the other side. So k is going to be 16. So we can rewrite this now. S equals 16t squared. And it says, how far will they fall in 4.5 seconds? So S equals 16, 4.5 squared, which when you work it out, you should get 324, and our label is feet. Okay. So moving on in a new direction, we're getting away from polynomials, going to look at the exponentials. So with an exponential function, it's going to be a base b, so it's going to be the number, some sort of number for our base, but it's going to be raised to an exponent that has a variable in it. So like f of x equals b to the x or y equals b to the x are going to be how it's going to look. Now, b is going to be either greater than 0, but it also cannot equal 1, because 1 to any power is just going to be 1. It's going to be a flat line. It wouldn't be an exponential then, but it has to be bigger than 0. So just some examples of how exponentials could go. Notice how we can get other things besides just a single variable in our exponents here. So we can get actually full out equations up there, and those would all be under the exponential. Now, the exponential function of f of x equals 13.49 times 0.967 raised to the x minus 1 describes the number of O-rings expected to fail when the temperature is x degrees Fahrenheit. Find the number of O-rings expected to fail when the temperature is 31 degrees. Now, what this is actually modeled after, and I'll leave it up to you if you want to look it up, but the Challenger disaster happened back in 1986, I believe, where the space shuttle, after about a minute into space, it exploded. Well, what happened was it was unusually cold, and some of these O-rings in the rocket boosters had failed, and that's what caused it to explode. So that's what this is modeled after. The significance of that is there was going to be the first teacher in space, so there was a lot of people watching, and a lot of heartache there because of this failure. But after that, they were able to figure out what was going on, and something like this didn't happen again. But to do this, when we're finding our temperature is 31 degrees Fahrenheit, that's going to be our x, so we're going to do f of 31. So in our calculators, we're going to put 13.49 parentheses 0.967 raised to the 31st minus 1 in. So if I grab my calculator, which of course I would not have one. Hey, this will work. This is what happens when kids mess with your desk. So if we start over here, so we're going to do 13.49 parentheses 0.967, closer parentheses, raise it up to the 31st. And I'm going to arrow over, make sure I'm out of it. And then minus 1. And when I hit go enter here, I'm going to get 3. Looks like 3.77. Now, we can't have a part of an O-ring. It's going to count as a whole O-ring that's going to fail. So this would be about 4 O-rings. So, again, that's what this is modeled after. Again, we should still not forget those that we lost in the exploration of space. But unfortunately, mistakes do happen and failures happen. So Big thing is they figured it out and they moved forward and got us back into space. And that's what we got to keep doing in life. There's your little PSA for the moment. Now, if we go to graph these, this is how this is going to work. We're going to actually pick 7. Now, when you do this in the homework, you won't have to, but I want to do 7 just to really show you how this is going to curve and how this graph is going to work. But I'm going to start by doing f of -3, and then go f of -2, f of -1, f of 0, f of 1, f of 2, and then f of 3. So if I did 3 in here, I would have 2 raised to the -3rd power, which is really going to be 1 over 2 to the 3rd, which is going to make this 1 over 8. Is where that's coming from. If I have to the -2 again flips it, but it's 1 over 2 squared, so it's going to be 1 over 4. To the -1st, we'll just flip it, and we're going to have 1 over 2. Anything to the 0 power. To the 0 power, if it's 456 to the 0 power, whatever it is to the 0 power, will always be 1. Now, 2 to the 1st would be 2. 2 squared, 4. 2 to the 3rd, 8. So what we're going to do here is the first number here, so -3 is your x. The y then is 1/8, which is what we got out. So when we go to graph these, go 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to extend my line up just a little bit. So the first one here, -3, and I'm going to be up an 1/8. So not very much. -2, be up a 4th, so a little bit higher. And then a little bit higher. And then a little bit higher. So -1/2, 0, 1. And now 1, I'm going to be at 2. 2, I'm going to be at 4. 3, I'm going to be at 8. So this graph, it's going to be coming along here. And then as we get closer, we're going to then start curving up and go almost vertical. And of course, I missed the last point. But that's kind of how these are going to work. They're going to be flat along the horizontal axis here, the x-axis. Not on it, but right above it. And then it's going to, as they get closer to here, we're going to start curving up. And then it's going to turn to where it's almost a vertical line. So that's what an exponential function graph will look like. Now, this was when we were above 1. Well, what's going to happen if we're less than 1? Well, again, I'm going to use these same ones. Now, I'm going to shorten it up a little bit. I'm going to go 5. This is what I would recommend you do. Do at least 5. Do more than the 3. You'll be able to see a little more of what's going to happen. So f of -2, f of -1, f of 0, f of 1, and f of 2. So if I do -2, this is going to be 1/2 to the -2nd power. So that's going to flip it to make it 2 over 1 and to the 2nd. So this is really 4. To the -1st, again, it's flipping it. And so it would be 1/2. 0, anything to the 0 power is 1. To the 1st is just a half. 1/2 squared then would be 1/4. So again, that first one is the x. The second one is the y. So on this one here, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6. So at -2, I'm going to be at -4. Or at +4, sorry. At -1, I'm going to be at 2. At 0, I'm at 1. At +1, I'm at a half. At 2, I'm at a 4th. And so now our graph is coming here. Leveling out there. So it's going to go the other way. So when we're above 2, we're going to curve up and increase. Or if we're above 1, I should say. If we're below 1, but not below 0, so between 0 and 1, then we're going to be decreasing as we go from left to right. So we're going to curve down and flatten out. So remember, while you're doing this, while you're watching this video, if there's ever a moment where you need to pause and write stuff down or rewind and hear me say something again, please do so. So help yourself out there. Now, these are some characteristics that we're going to come across here with exponentials. So first off, the domain of an exponential is going to be all real numbers. Any x will work as long as it's a real number. The range then is just going to be all of the positive numbers. Notice how it's not including 0 or any of the negatives. It's just the positive numbers. We're always going to be above that x-axis. All the graphs are going to pass through the point 0, 1 because anything to the 0 power will be 1. If our base is greater than 1, as we go from left to right, we're increasing. If we're between 0 and 1, we're going to be decreasing as we go from left to right. Now, an exponential function is always going to be 1 to 1, so there's only one x for only one y. There's no repetitions of any value, the x or the y. There's only one that works with each one. It's also going to have an inverse, so we'll be able to find that inverse. So it would pass the horizontal line test. And then the graph will approach, but will never touch that x-axis. So we're going to have a horizontal asymptote at y equals 0. So we'll go along it, never actually touch it though. Now we can transform these just like we could quadratics or polynomials. So if we add or subtract something to the outside, that's going to move it up or down from that original graph. So it's always going to go the same way that you would think. So positive would be up, negative would be down. If it's inside the exponent that we're adding and subtracting, it's going to shift it left and right, but it's going to be opposite. Positive shifts it left, negative shifts it right. If we have a negative on the front here, we're going to reflect across the x-axis, so it'll flip it down. And if it's in the exponent, it'll flip it left and right, so it'll flip it across the y. And so if it looks like it's increasing, after the negative, it'll look like it's decreasing. Timesing on the outside will make it look taller or shorter. Timesing in that exponent will make it either wider or skinnier, depending on which way it goes. Now again, anything in the exponent goes opposite, so the bigger the number, the skinnier it is. The smaller the number, the wider it is. So if we look at one like this, how would this graph change from 3 to the x compared to 3 to the x plus 1? Well, this plus 1 is on the inside, so it's going to go left to right, and because it's added, we're going to go left 1. Okay. So inside the exponent, left to right, and it's always opposite, so plus 1 is actually to the left, and so it's going to go the 1 because it was added. Quick one here. So what would the graph of g of x equals 2x to the x minus 3 change from f of x equals 2 to the x? Now, we have a minus 3 on the outside. We're outside the function, so when it's on the outside, it goes up and down, and it goes the way you think. So this will be down 3. Okay. So can transform them, can shift them, can stretch them, just like we can with quadratics. Now, the natural base e, so the number e here is defined as the value of 1 plus 1 over n raised to the n, as n would go to infinity. So as n gets as big as it can, what value would we get? Now, they approximate that value to be 2.72. Now, we'll get more into this later on in other lessons, especially as we get to working with natural logs and how these work with them. But this is a natural base number that they use for different things. A lot of times it gets used in problems like this where it's dealing with growth, exponential growth. So in the year 1969, the world population was approximately 3.6 billion people with a growth rate of 2% per year. The function f of x equals 3.6e raised to the 0.02x, and this should be describes, not decries, describes the world's population in billions x years after 1969. So find the world's population in 2020. Now I know 2020 is come and gone. So we could actually look this up and see what the real one is. But we're going to see what does this population, what does this function predict the population will be. So first off, we're going to do f of, well, what is our x? X is going to be how many years after 1969? So 2020 minus 1969, we get 51. So 3.6 e raised to the 0.02 times 51 in our calculator. So grab my calculator here. I'm going to clear out what I got. So I'm going to do 3.6, and it's going to be second ln to get the e. Now, it raises it and puts it in parentheses. This is good. Take this whole parenthesis and put it in. So 0.02 times 5.1, close that parenthesis. Hit enter, and we get 9.98. So 9.98, and this is billion people. So according to this, we should have got to 9.98 billion people. I believe we're at 7.8 billion. So we're not that far off. But that's a lot of people. And really over 50 years, how we practically double. But we're even a little bit above double. Kind of crazy how the world has expanded. Now, one actual practical, more practical, not that the other one's not practical, but a more practical application of this where you may actually use this in your life is with compound interest. So compound interest is going to be the interest computed on your original investment as well as any on accumulated interest. And it's going to be something that's going to be done periodically throughout the year. So A is going to be our amount. So equals P, our principal, so the amount that you're going to put in, times 1 plus R. R is going to be your rate, interest rate, but it needs to be as a decimal. So you have to convert it from a percent to a decimal. Over N, which is the number of times per year, it's going to be compounded. So if it's semi-annually, N would be 2. If it's annually, it'd be 1. Quarterly, 4. Monthly, be 12. I'm trying to think of other ones like bi-monthly, so 6, sort of a thing. So that's what you would use for that N. And then it's raised to the NT. T again is time, but it's years invested. So we can also use A equals PERT, where we're doing continuously compounding. So it's infinitely amount of compounding periods. It's automatically always compounding and building on itself. Now, you decide to invest $8,000 for 6 years, and you have a choice between two different accounts. The first one will pay 7% per year, and then it's going to be compounded monthly, where the second will pay 6.85 per year and be compounded continuously throughout the year. So we're going to set these two up. So the first one, so A would equal 8,000, my principal, times 1 plus, my rate is 7%, so move the decimal twice, and I have 0.07 over, because it's monthly, over 12, raised to the 12 times T, which is 6. So we're going to put that in our calculators. So 8,000, parentheses, 1 plus, now I'm going to do, it's not going to like 0.7 in a fraction, so I'm going to do parentheses 0.07 divided by 12 and close it to make that fraction. I'm going to close it again and then raise it. 12 times 6 is 72, so I can make this to the 72nd. And when I hit enter, I have 1216,0864. So $12,160.84. Not bad for 6 years. You're getting a little over 4,000. So this is where it's important to save money, because it does build, and then you're prepared for when you need emergency stuff, or when you decide that, hey, I want to upgrade houses, vehicles, whatever. Always good to have savings. There's your second PSA. So second one here, we're going to use the A equals PERT. So principal is still 8,000. E, I don't need this parenthesis. E raised to the R, which is be 0.0685, because we're 6.85%, so move it twice to make it a decimal, times our 6. So in here, 8,000. Second ln to get my E. Now we're already in parentheses, so 0.0685 times 6. Close the parentheses, hit enter, and we have 12,066.60. So $12,066.60. So, which one is better? Well, the first one. Now, this is where compounding continuously, you would think, well, it's always compounding, so it should build faster. Not always the case, but for the longer run, it does pay off a little better. Shorter run, not as much. So, that's the lesson 3.1. Please let me know if you have any questions. You can always email me, pan me, send me a message on Google Classroom. Otherwise, we'll talk to you later.